most people think of synthesizers, they're thinking of subtractive synthesis. Throughout the analog, digital, and software days, subtractive synthesis has by far been the most popular and used synthesis format. So what exactly is subtractive synthesis? Like its name suggests, subtractive synthesis works by subtracting things from harmonically rich sounds. The harmonically rich sounds which act as the building blocks of subtractive synthesis are called waveforms. Waveforms are created via circuits known as oscillators. The standard subtractive waveforms are sine, triangle, sawtooth, ramp, square, and pulse. Each of these waveforms contain differing harmonic content and have their own unique sound. For example, sine and triangle waves are very mellow sounding, whereas sawtooth and ramp waves are very harsh and in your face. Finally, square waves have a hollow richness to them, while pulse waves sound hollow and rich or nasally depending on their width. These waveforms are then subtracted from in three ways: in the frequency domain, the time domain, and the amplitude domain. Let's start with the frequency domain. The most common way in which we subtract frequency content is through filters. Most commonly, subtractive synthesizers feature low-pass filters. Low-pass filters cut out high-frequency content above a certain variable point known as a cutoff frequency. Although low-pass filters are by far the most common subtractive synthesis type, a few others exist which are worth mentioning. The next most common filter type is known as a high-pass filter. High-pass filters are the exact opposite of low-pass filters in that they cut low-frequency content below the variable cutoff frequency. The next two filter types are known as bandpass and band reject filters. Bandpass filters cut out frequencies above and below a set frequency band, whereas band reject filters only cut out a narrow frequency band, leaving the frequencies above and below it intact. Almost as important as the filter cutoff frequency is a parameter known as resonance. Resonance is basically a feedback circuit which emphasizes the cutoff frequency and immediately surrounding frequencies. Resonance is used to add an animated quality to the sound that can be achieved no other way. Next, content is subtracted in the time and amplitude domains via a number of different parameters. The first parameter we'll cover is the envelope generator. An envelope generator typically contains four parameters: attack, decay, sustain, and release. When routed to an amplifier, the attack parameter corresponds to how long the sound takes to reach its set amplitude. Decay and sustain work in conjunction in that the decay parameter designates how long it will take the sound to fall to the set sustain point after completing the attack cycle. Finally, the release control designates how long it will take the sound to fall in amplitude once a key is released. Envelope generators are often used to control a synthesizer's filter as well. When controlling a filter, the envelope will act the same as it does when it's controlling an amplifier, except for instead of controlling amplitude, it will control the filter cutoff frequency. It's also important to mention that many synthesizers offer the ability to control pitch via envelope generator. The last parameter we'll cover in this brief introduction is LFOs, or low-frequency oscillators. An LFO is a near identical circuit to a traditional oscillator, but creates a pitch that is below the audible frequency range. These low frequencies are used as control sources rather than audio sources. Using an LFO, one can modulate pitch for vibrato, amplifiers for tremolo, or filters for filter sweep type effects. Typically, the depth of the LFO is set by a modulation wheel or a potentiometer. The following videos will explore a variety of subtractive synthesizers and show some of their unique features and sounds.